Right, guys, taking from our previous presentation, this was about calculating calculating roots of complex numbers, which essentially those are equations involving complex variable. So this is where we ended. But now I want to take advantage of this kind of an expression, representing a number in exponential form. This is this one. In this case, this number can be presented in exponential form using the argument. That is taking us to what? To think about logarithms of complex numbers. Now, if you look what I've written there, I've written capital letter N, Z, and next to it I thought also and LZ. If you look at this notation, is the one notation for ln, which we know, which I've been using for complex numbers. The properties of ln as a logarithm function still apply here. But when I look at L, capital letter LZ here, I'm talking about something slightly different. What am I talking about? Let's say I've got Z represented exactly the way we represented it when we're calculating roots. That is R e to the power j theta plus 2k pi. What I'm talking about here, I'm talking about that idea of rotating a number around the origin, adding to 1 pi, 2 pi, 3 times 2 pi, it's 2n pi. That's exactly what gives us the same number altogether. Now, if you think of the idea of calculating a logarithm there, what did you do? You would say, let's use this one first. I would say ln capital letter Z equals to capital letter ln R e to the power j brackets theta plus 2k pi. Now, this, we can look at it as a ln of m times n. What is our m? Our m is R, and our n is this exponential expression. Are we there, all of us? Do you see two numbers there? A positive number, R, and that. Then, when you get there, applying the rules of logarithm now, can say ln R plus ln E j theta plus 2k pi. Now this is ln, this is E, a function and its inverse. What does it do? It delivers the argument, isn't it? So this one is a positive number. I may as well here write the usual ln because this is a positive number. But here I'll apply that. Then I've got plus j theta plus 2k pi. Now let's listen to the reason why did I write this way. When you use the ln this way with real numbers, this was a number, one number. Now please pay attention to what I'm saying, guys. Pay attention to what I'm, stop writing, pay attention to what I'm saying. When you use the ln this way, this was a number, one number. But now I'm using ln capital letter this way for complex numbers. What I'm trying to say, actually, I'm trying to highlight to you that this is now not a number, but a set of numbers. Do you see the set of numbers? This k is an integer. If I count from 0, I will have this first number, I'll have here ln r plus j theta. Then if I give k1, I'll have ln r plus j 2 pi. But in this case, k is an integer. It could be plus or minus altogether. Plus or minus altogether. So here I can actually use plus or minus. So I'm getting what? This side I'm getting positive, negative, positive, negative, positive, negative. So this is a set. So now calculating ln of z, you don't get a number, you get a set of numbers, which maybe it can be a good task to investigate. If you plot these numbers, how do they look like on the Hagen diagram? It's a good homework to do that. Now, when we talk of this small ln of a complex number, we are talking here about what we can call the principal logarithm of the complex number. Principal logarithm of z, the complex number of z. Do you understand what I'm saying? Do you understand what I'm saying? I'm saying if I use a small letter or small letter ln of z, I'm talking about this principal logarithm of z. And this is unique. What do I mean by unique? I'm saying there's only one, and that is only one principal logarithm of z. But if I just talk of logarithm of z, there are infinite numbers, like as you say, as you run k across what? The integers. Is that understood? Now, the problem now is, for these ones, I'm using this argument. What argument am I going to use for the principal logarithm? That's the question. Do you hear the question? I'm saying for these numbers, infinite numbers, I'm going to have different arguments depending on k. This is the form of the argument. Now the question is, which of these arguments are we going to use to determine what? The principal logarithm. Do you hear the question? Do you hear the question? Can you repeat the question to me? But my sister, you don't need me to read your face before you can say you don't understand. You must tell me exactly you don't understand when immediately you don't understand. Please guys, I don't know whether you got this message clear. You have got the right to stop the lecturer and say, oh, I don't understand. From there onwards, I don't understand. That's your right. Are we together? Yeah. Don't feel bad by stopping the lecture and say no. Say, or madam, whoever, I don't understand from there. Now, point number one. I said, if I'm using this notation to calculate the logarithm of z, I'm not talking about one number. I'm talking about a set of numbers. How do I get those set of numbers? I get them in terms of the argument like this. And in this argument, you remember where we got it from. We said if you take a number, rotate it 2 pi, you get the same number. Another 2 pi, you get the same number. So all the factors of 2 pi there are going to work for the same number. Now, if we now calculate a logarithm, we get this thing in this form here. This is a unique number because it's a positive number. But now this gives us infinite numbers. K is running across the integers. So there's plus minus k here, plus minus k. So these are infinite numbers. Are you getting that? But then I'm also giving you this notation and say this notation will stand for what we call principal logarithm. And then immediately there, we've got all these infinite arguments. Now for the principal logarithm, which argument are we going to use? That's the question. Did you get the question? Did you get the question? What is the question? Among which ones? Among those infinite arguments which depend on k, which one are we going to choose? And they say this one is the argument we're going to use for the principal logarithm. Now we say, therefore, ln z principal logarithm, let's just say log of z, theta, the argument, must be between minus pi and pi. What does that mean? Look at this. I have a number, let's say I have a number here like 1. No, let me not use that one, sorry. Let me use a different number. Let's say I've got a number there. I can move from this number this way, in this direction. Let's say I start from here, 0 minus, this is minus pi. Yeah, sorry, there's an error which I did there. I'll show you what is the error. I will not correct it now. This will be minus pi. But if I move this way, this will be pi. Altogether. But now, you see that now, if I go that way, I look like I'll touch this line twice. So not to touch the line twice, we remove equality here. That's what I'm correcting there. We remove the equality there. So, in other words, you cannot allow your angle to be more than pi. Because now if you allow this now to go more than pi there, you are now wrapping around altogether. So as long as I've got a number, and then I find out if the argument I can use is between that, then it's fine. Like for example, this angle, if this number, I'm dealing with this number, this angle here, theta 0, will be an argument between, in this range. Because if I start from 0 here, and they go this way, that's what? Minus pi, up to pi. If I go, sorry, that's pi. If I go this way, and then open there, that will be minus, almost minus pi. Then I open that thing there. So that's what's happened there. So as long as you choose an angle which is between those two and use it in logarithm for principal, then you are going to get that as your principal argument. I think our time is almost exhausted here. We'll actually look at examples on this one in our next presentation. For now, thank you for listening. As usual, I hope you enjoyed the lesson. If you didn't, it wasn't my intention.